So I'm starting the recording. There's that. And before we get going on our lecture, we have an announcement. Peter, you want to come up here and tell all these people about this great panel
Sure.
tonight?
Tonight, actually more this afternoon, from 3 to 5, there's an event called Go Sustainable. And it's being held by the Graduate Students Council and some other student groups and some of the OSU offices. And pretty much it's a town hall format and a panel. And what we're going to have is 3 discussions, one revolving around energy and transportation, one on the natural and built environment, and a third one on community engagement, which I actually will be speaking on. And so we'll have, each panel will have some OSU faculty and some students, and to me to kind of start the conversation some more and get everyone in the same room regarding OSU and sustainability, so people can ask questions about what's going on with geothermal. We're going to ask questions about our plans for the future, so kind of what Scott Potter did, and kind of expand it a little bit. So it's 3 to 5 in the Ohio Union, and the Great Halls rooms 1 and 2, and there'll be free vegan snacks, and so I encourage you to come.
We know why vegan, right?
Yeah, less impact.
Less impact. Thank you. Great. I'll try to send out an email about that so the people who haven't watched the video before today will get a chance to go to it. Okay. So let's see where we are. This is the part where we talk about how does it all add up. And we'll start talking about engineering cars. All right, so we finished the stacks. We did a stack for England and we did a stack for Ohio. And we found that for England, the consumption was slightly higher than production, and I think Ohio was kind of a wash. No, we didn't put nuclear in there yet. And then we also tried to get our stack numbers. So we made these estimates of how much energy we'd use. Then we tried to look at other sources to figure out if we were in the right ballpark. And we came to the conclusion that, yeah, we pretty much were. So for United States, somewhere between 250 and 300 kilowatt hours per day per person seems like a reasonable consumption figure. So here's the red stack again. It was based on how much energy an affluent person uses, because it assumed that this person had phone chargers and stuff like that to plug in, and that they had a house they could heat. Are these numbers valid? So McKay went and he looked at some other sources, and he found that they also say most energy is used for transport and heating, which is consistent with what we found. Well, that's so far so good. So we take a closer look at transport. So in our estimate, we found the energy footprint of driving a car 50 kilometers per day was about the same as flying from Cape Town to London 1 time per year. Question is, maybe affluent people fly more. You know, maybe we're going to Cancun more often or something like that. Here's some great numbers. Road transport is fueled by petroleum, 22.5 kilowatt hours per day. Railways, fueled by petroleum, diesel fuel. Water transport, fueled by petroleum. Aviation, fueled by jet fuel, petroleum. Other modes that are going by electricity. So energy from this figure used by transport is about 31.6 kilowatt hours per day per person. So do affluent people fly more or use more energy? Let's take a look. So here is a plot of power consumption in kilowatt hours per day per person versus gross domestic product per capita in dollars. So this is 10,000, 20,000, 30,000, so forth. And let's find the UK. Here is the United States up here. Hey, look. This figure is about 250 kilowatt hours per day per person, consistent with our guesses. Here's the UK. I'm following this arrow. It's this red dot right here, I believe. It looks like it. This red dot right here, and this is saying maybe 125 kilowatt hours per day per person. Here's some other countries around it. Denmark, Ireland, Austria, France, Germany are in this area. So that says that the UK is a fairly typical European country. So if you're a European, that's a good case study. Let's find Hong Kong. Has the same GDP as the UK, so somewhere along here it is, Hong Kong, right here. But less energy consumption per person. There's Hong Kong. So what's special about Hong Kong? So let's look it up. Here's energy consumption by sector for Hong Kong, and it says that 57% of it for transportation. Mostly transportation. Almost all of the energy, 95% of their energy comes from petroleum. Here is million tons of oil equivalent. Fossil fuels, you can't even see. So there's fossil fuels is the blue, and there's a very thin line of these other colors on here. Basically, they're using a lot of petroleum. Again, a lot of transportation. Let's see what else there is. 17% commercial and public services. It's a teeming metropolis. 17% is industry. 1% is non-energy uses. 8% is residential. And I don't even see agriculture on there. Well, duh. It's a giant city. Let's look at some other countries. Here's an interesting one. Trinidad and Tobago. So they've got a very low GDP, but they've got a pretty high consumption, higher than us per person. So what, do you know where that is? Trinidad and Tobago? 2 islands? Okay, you're looking like you do? Okay. So, most of their energy, 85% of their energy is industry. Their energy use has drastically increased recently. Clunk, here. And appears to be mostly industry. This 12% is transportation. There's that transportation thing again. Purple is residential, and you can't even see the rest of these things on here. So we can't even tell, like, agriculture, commercial services are negligible here. Trinidad and Tobago, industry. I have no clue what industry they have there. Does anyone know? Has anyone ever been there? Me either. Iceland. Here's an outlier. What are they doing? Look at their humongous consumption per person and sort of a modest GDP. Well, it's a good, healthy GDP. It's a little bit less than ours. What do we think's going on with Iceland? Why so much energy per person? What would you guess?
Weather.
Yeah, weather is what I would guess. Let's find out. Iceland, whoa! Iceland gets 70% of its energy from renewables. 30% here, oh, sorry. Here's fossil fuels as blue. This dark brown is hydroelectric. And this orange is other renewables. Whoa. And that's because it's a hotbed of geothermal energy. If you want to be a geothermal energy guy, you want to live in Iceland. That loads of that, and they have lots of hydro, so they're sitting pretty. Though they use a lot of energy, 30% of that is industry. Compare that to 85% for Trinidad and Tobago. 27%, residential. I'm thinking heat. 7% is non-energy uses and others. 16% is transportation. Small place. Not as much energy used for transportation. I'm thinking a lot for heat. 15% is agriculture. What do they grow in Iceland? Ice. I have no idea. But a quarter of their energy is a quarter of their renewable is from hydro, and 3/4 from geothermal. So they can actually pop hot water directly into their homes or physical plants or whatever to heat the buildings. And if you live in Iceland, that's a good thing. So they're sitting pretty. They can have all the energy they want. They're not hurting anybody. India. Let's see where India is. Whoa. Very low GDP and very low consumption. Let's see what's going on with India. India. This is 56% residential. So I'm thinking heating, probably, maybe some cooling. 27% here. Sorry. Oh, is industry. 12% is transportation. They have a little bit of agriculture. So this says mostly agriculture. That's not right. That's on drugs. Don't pay any attention to that. Lots of renewables. So here's a look at them. Fossil fuels. They got a little sliver of nuclear, a sliver of hydro, and other renewables. The orange part here, this renewables, is almost all biomass, including burning firewood and dung and whatever. So that's where they get a lot of their heat. It's interesting to see how all these different countries are. So what do all these countries have in common? Yes, right. Look at everybody is increasing their energy consumption. What else do you think is increasing everywhere in the world?
Population.
Population. Gee, I wonder if there's a connection. This is Iceland. Think they figured out, so this is 1991, 81, so this is about 2001. This is what it probably, I'm guessing, that they started using geothermal in a major way. Excuse me. All right, so let's look at the green stack. You recall, McKay's estimates are wildly optimistic. He let you put solar, thermal, and PV on the same roof at the same time. He says, let cost be no object. And we noticed in our Ohio stack that where we saw the most potential was PV farm. We don't have any PV farms. And we speculated here in class that this is probably because of the cost. So this would be if cost was no object. And then, what other assumptions did he make? Well, some assumptions were he assumed that nobody would object to covering 5% of England with windmills and another 5% with solar and so forth. That society didn't care. So this is interesting. Here's McKay stack. Then he went to these other organizations. I'm going to use the mouse here to point. This is IEE, the Institute of Electrical Engineers. Their estimate was 10 kilowatt hours per day geothermal, a little bit of tide, a little bit of waves. They didn't believe in deep offshore wind. They believe in a little bit of shallow offshore wind. Biomass, they believed in a little bit. They said no to PV farms, PV, solar heating. They allowed for a little bit of wind. This is the estimate by this organization. Here's Tyndall. And on the next slide, we're going to look at who these organizations are and try to understand what their biases are. Because maybe they don't like green energy and so they're trying to be pessimistic. Tyndall says, oh, we'll give you a little bit of tide, a little bit of wave. We don't believe in deep offshore, little shallow offshore, hydro negligible, energy crops small, PV tiny bit of wind. IAG, similar things, tiny tide, little wave, little offshore. Nobody here believes in deep offshore except maybe CAT, whoever that is. These guys here, PIU, whoever they are, and we'll look and see who they are in a sec, believes in energy crops and waste incineration, landfill gases, so they think that has a lot of potential, even more than McKay thinks, but they don't believe in some of these other stuff. So if you took all these stacks and squashed them down, there wouldn't be a lot of potential. Now let's see who these people are. IEE is the Institute of Electrical Engineers, is a British professional organization for, yes.
Were those estimates taking in consideration, like they dropped the assumptions, like they're kind of taking more the practical route, like how realistic really would it be to put PV farms around, and they figured like it's not economical and people wouldn't like enough, so we're going to say no to it. Are those groups dumping those assumptions that McKay had earlier and saying we're applying this more practically?
Yes, I think, I haven't read what they actually wrote, but I believe that these estimates are based on what's practical. And so they probably are taking costs into account, which is probably why this is largely missing. So anyways, IEE, Institute of Electrical Engineers, so they're going to know things about the efficiencies and stuff like that. They probably don't have any particular reason to be biased for or against green energy. The Tyndall Center for Climate Change Research, here's what they say. We bring together scientists, economists, engineers, and social scientists who are working to develop sustainable responses to climate change. We work not just within the research community, but also with business leaders, policy advisors, the media, and the public in general. So what do you think? Do you think that an organization like this would be likely to be biased for or against sustainable energy? You're saying yeah, so would you think they'd be inclined to be biased for or against? For, okay, I agree. IAG, the purpose is to provide internal peer review of analysis by government and related bodies of the impacts of policies that affect the government's objectives to reduce greenhouse gas emissions and promote sustainable and secure energy supply. So again, I think this is a group whose biases are probably toward green energy. So their estimates are much more pessimistic than McKay's. PIU, Performance and Innovation Unit, as near as I could tell, that's a committee of the UK Cabinet Office, whatever that is. So who knows if they have a bias or not. Center for Alternative Technology. CAT is an education and visitor center which demonstrates practical solutions for sustainability. We cover all aspects of green living, environmental building, eco-sanitation, woodland management, renewable energy, energy efficiency, and organic growing. I'm thinking those guys probably biased toward sustainable energy. So that worries me when I see that even though they are in favor of it, they're not as optimistic. And McKay is widely in favor of, but also widely optimistic. All right, so what about regular people? So people, some people have reactions to, well, yeah, you can have a nuclear waste dump, but not in my backyard. Similarly, some people don't want to look at windmills. Personally, I think this is nuts. I think those windmills are very beautiful. I love driving through northwestern Ohio and just watching them all and crashing because I'm looking at the windmills. But some people don't like to look at them because it spoils the scene. I heard an interesting argument, well, would you rather look at windmills or transmission lines? Of course, yeah, both. But we've accepted transmission lines. Some people say that windmills kill birds and bats. Biomass, well, I don't want you to grow whatever it is, switchgrass in my countryside. These are arguments that McKay puts forward. Solar panels, some people say they cost more to make than they produce. As you guys know, you have to take into account the energy it used to produce it, how long does it last, energy to get rid of it, that whole life cycle analysis that we talked about before. And the answer you get depends on over what length of time you amortize that. So you can make this number come out differently depending on what your bias is, I suppose. Solar panels, I don't think that they fail easily. There's nothing in semiconductor physics anyways that would make them fail unless the connections break or birds poop on them and they don't get clean. Too expensive is an argument, and that's applied to a lot of the sustainable sources we've discussed. Yeah, seems reasonable. That's why we're using coal, because it's not expensive. So McKay says, well, he crossed out geothermal, too immature. He left tide. He crossed out, what's that say? Waves, too expensive. Deep offshore wind, not near my radar. Shallow offshore wind, not near my birds. What was this? I don't even know what that was. Not in my valley. Biomass, not on my countryside. PV farm, too expensive. PV, too expensive. Solar thermal, not on my street. He's got citations here. Wind, not in my backyard. Well, there are people who disagree with a bunch of these things. So after he takes the public consultation, he concludes that they could realistically in England get that much sustainable energy. I don't know what it would be here. What do you think well, first of all, what do you think could happen to make people more accepting? How could we get people to be more accepting of these alternative sources? Yeah? Money, he's saying. So you're thinking maybe that as energy becomes more expensive, when we start to run out of oil and coal, and these other things start to become more cost effective, people will accept looking at a windmill?
Yep.
I think you're right.
Or if they get tax incentives now.
Sorry?
Or if they get tax incentives now.
Tax incentives now. So that's why we're putting up wind farms, is because there's incentives to do that. So here's his social reality. He's figuring a total of maybe 18 kilowatt hours per day per person in England. So how common are these views? So here is the results of a survey in the United States. Which is the best way to help solve the energy crisis and make America less dependent on foreign oil? A, building new nuclear power plants. B, drilling offshore in Alaska. C, developing renewable energy sources like solar power, wind power, and biofuels. D, releasing oil from the Strategic Petroleum Reserve. Or E, mandating high mileage on cars. So I'm going to use the mouse again to point to this. The red thing is renewable energy. So half of Americans, Colorado, Michigan, Minnesota, and Wisconsin, more than half thought renewables is the best way to solve the energy crisis. This light blue color down here is drilling offshore and in Alaska. This dark blue guy is nuclear. And these little guys down here are strategic reserves and high mileage cars. So people in the United States at least are saying they can accept renewable energy. Reality check. So another poll shows 87% of Americans favor wind energy rather than oppose it. But then someone says, okay, well, how much are you willing to pay? 34%, well, they're not willing to pay for it. You know, they could accept it, but they're not willing to pay for it. 17% said they might pay up to 5% more. 5% would be willing to pay 20% or more than they do now. Nobody's saying if you double the cost, I'm willing to pay for it. Or anything close to that. So possibly Joe Public doesn't fully appreciate what's at stake. I think that's highly likely because Joe Public hasn't taken this awesome class. Not everyone believes in global warming, at least not yet, and a lot of people might believe in it, but they don't care if they can make money. So anyways, this is why the Department of Energy is sponsoring this course. So they're paying for it because they want us to inform Joe Public, educated Joe Public, about these energy issues so that you can help drive policy in the future and vote intelligently. When I say intelligent, I mean like you agree with me. Okay, so here's a clicker question. What percent of the consumed energy was generated from renewable and nuclear sources in the UK according to the data in the book? 0.5%, 4%, 10%, 30%. How many people think it was a half? Nobody says that. How many people think it was 4? How many people say 10? 1. Nobody believes 30? You do? Okay. Did you read the book? I haven't read. I've read this part, but I don't remember the answers. I'm hoping it's on here. Ha! 4%. Phew. Dodged a bullet. That was, however, when that book was written. I don't know if it's increased. The U.S. there's a huge difference between. Well, there's a significant difference between today and 2 years ago. Renewables in the U.K. So here's all the renewables in 2006 in the UK. Basically a kilowatt hour per day, and of that. Some is wind, tiny solar, biomass. This is landfill gas, sewage and waste incineration. This is biomass co-firing, biomass wood in homes, biodiesel, large hydro, small hydro, and offshore wind. And then nuclear, they're at least in 2006 getting much more energy from nuclear, about 3.5 times as much. Renewables in the US, this is 2008 data. And here's stupid stinky petroleum, natural gas, coal. Here's the renewable. For us, a significant fraction, more than half, this is 53%, was biomass. 34% hydropower. We've talked about how we put in hydro in all the easy places to put it. There's some wind, some geothermal in those parts of the country that can do it, and some solar. According to this, in 2008, we were about 8% nuclear. U.S. renewable energy supply. So this is 2012 data. So these 2013 and 2014 are projections. And here, this brown is hydropower. So you see that the size of the brown stack, it's interesting, and it went down here. Oh yeah, extra wet year in Pacific Northwest, so they got a bunch of extra energy, and then we had a drier, more typical season this year. So the hydro, the capacity isn't necessarily changing. How much energy we get is somewhat seasonal here. So projections are that that's going to be about the same. This orange here is wood biomass. I think that's interesting. The red is increasing. Red is liquid biofuels. So I'm thinking more biodiesel is my guess. But it looks like it increased here and then it's staying about the same size these years. Wind power, ooh, looks like we're increasing wind, and it looks like people expect us to increase wind. That's consistent with what we've been observing, wind. The green, other biomass, that looks like it's staying about the same. Geothermal is the blue. It looks like it actually went down here a little bit. It's not changing much. and then solar is gray, and it looks like it's starting to come in a little bit. So if I were going to say what are we increasing the most, I'd be looking at wind. So what are our choices? Well, we can do business as usual. Here's the result. We could just keep on going like we're going and burn to a crisp. We could invest in sustainable energy, which is going to cost money. We could cut back on lifestyle. Here's a low energy lifestyle. No thanks. We could reduce population. We came close to this last week. And it's okay with me to reduce population as long as there's nobody I actually know or lives near me. If you want to reduce population, on Moon or something like that, that's okay. But I don't think that's going to be a widely acceptable solution here. Re-engineer transport, heating, and cooling and stuff. Maybe we can re-engineer so we don't have to cut back on our lifestyle significantly, so that we can use less energy, so we're not doing business as usual, and we don't have to reduce our population. It'd be great to maybe not increase our population anymore. Cutting back on lifestyle could mean going back to bow and arrow days, or it could mean changing our lifestyle so that we don't use as much energy. So the second part of this course is going to be about that. We've looked at the green stack, and now we're going to look at the red stack. What can we do to make the green stack any higher? Can we make the red stack any lower? So McKay's point is that if we're going to make a difference, these renewable facilities, they have to be country-sized. It isn't going to be, I'll put a PV panel on my house and I'm good. They're going to be large, they're going to be intrusive, we're going to see them. If we're going to put up solar panels on 5% of Ohio, we're going to know where they are. They may make noise. We saw that some people say windmills make noise. I don't think they make much noise. The wave ones made noise. The other ones do too. They may have an effect on the environment. They may kill birds. They may do other things. They require major investment up front. So then the question is, who should pay? Should it be the people who got us where we are now, or the people who are coming up now who are demanding the extra energy? And how long do we have? We don't know the answer. I'm thinking not long. Key point number 2 is that part of the problem, and we talked about this before, is the number of people in the world. So everybody wants to improve their standard of living. I don't blame them. They should all have what we have, and they all want that, and it takes a lot of energy to support that kind of lifestyle. So it's not just transportation, but food, heat, water, medicine, etc. for everybody. Air conditioning. So we have to do something. We have to make some hard choices. And so we need people who understand the issues. Again, that's the point of this course. But we want those understandings to be based on numbers and facts and critical thinking, and not just, well, I don't know, why don't we just put up windmills and we'll solve the problem? So now we already know that's not going to be enough. It's not just based on what I heard at the coffee cooler or something, and not based on sound bites in the media. Time out. I got an email from some producer for ABC television who wants to produce a show about people who believe they can see dead people, and he wanted someone with a PhD in engineering to come and do measurements of the paranormal in the RF and I forget what other frequency range, but it had to be someone who didn't automatically discount the existence of the paranormal. So this is the kind of stuff you see on television, right? Because why? Because it sells advertising, not because anybody believes it. I hope that guy doesn't believe this. But anyways, just saying that what's in the media is not necessarily intended to be for our benefit. So if it's not possible to maintain our current lifestyle without fossil fuels, or can we change something? Here is a review. Oh yeah, I forgot to mention about the midterm. So you probably say, what? I got an email, there's a midterm? Did you get that email? Yeah. Don't panic. The reason that I assigned it so suddenly is I thought there was more time, but I wanted you to be able to finish it before spring break so you can take a break at spring break and lay in the sun. So you have 2 weeks to do it. So we knocked out one of the quizzes, so you don't have to worry about that. The homework 5 is due today? No, next week. Homework 4 is due today, isn't that right? Yeah. I just posted homework 5. Do that one first, and then that will, some of the midterm may be related to what you do in homework 5, so you can see how to do some of the problems. But the midterm, you should just think of it as a little bit longer homework problem. It's the same style of questions. And also, nobody has come to visit me during office hours, so if you're having any troubles with the homeworks, and you distance people too, you should come and see me, because I know how to do them. Okay. So anyways, to review, in case you had a midterm coming up, energy is measured in joules, kilowatt hours, kilocalories. Here's some conversion factors. Power is measured in watts, kilowatt hours, or kilowatt hours per day. Volume is measured in liters, mass in kilograms, weight in newtons or pounds. Brightness is measured in lumens. Facts to remember: pollution, 5.5 gigatons of CO2 per person per year. What? Isn't this gigatons? No, it must be tons. I have to go back and look.
That's per person,
Per
right?
person, maybe that's what it is.
Gigaton would be,
That'd be too much, yeah. U.S. is about 4 times higher. Calorific value of fuel, for coal and petroleum, ballpark number, 10 kilowatt hours per liter. Maximum sunlight power density on the surface of the Earth, 270, that's at the equator. A strong wind would be a speed of about 12 kilometers per second. Bowling Green, the average was about 6, I think. And then when you see nano, micro, milli, kilo, mega, giga, and tera, these are the exponents that go with them. Just a review. And this is the end of part 1. So you should be starting to read part 2. But part 2, and we're going to do chunks of part 3. You don't have to go read the chapters in part 3. Part 3 gives a little bit more technical stuff. We'll grab out of there what we need. You should be reading part 2, though, because that's where the background is, and we'll proceed from here. So we got to figure out now, we can increase the green stack. Basically, we need money for that. We can decrease the red stack. I think we should work on that. We should do both. We should definitely do both. We should not do nothing. And I had a friend who was a psychologist who always used to say, not to decide is to decide. So if we decide to do nothing, we've just decided to heat up the earth and burn to a crisp. So we got to do something. That's my view. So increasing the green stack, we found that we require many sustainable energy sources. There's no one magic bullet. We're going to have to deploy them on massive scales in order to meet our energy needs. Even if we decide we're going to do that, it's going to take time and money. And we can't do it, even if we decide that we're going to go all renewable, we're going to put in all the money it takes, we're going to pay for 5% of Ohio with windmills, another 5% with solar. We still can't do it fast enough to prevent too much global warming to recover from, based on data we saw earlier in the semester. Sustainable readiness. Some possible sustainable energy sources are not yet cost effective. So like clean coal has been demonstrated, but not on a commercial scale. Carbon capture and sequestration. Some exist only on paper, like people have proposed deep offshore wind, but nobody's doing it. People have proposed shallow offshore in Lake Erie, but it hasn't happened yet. Some kinds of energy are more well established, so even the ones that are more well established, maybe we can improve the efficiency. All of these things require engineering. This is why you have engineers. You're welcome. And we could change our lifestyle, so we could go back to some historical lifestyle with bows and arrows, but then we can't sustain all the people on the earth. Even if we all went back to doing that right now, we could not grow enough food for everybody, apart from the energy consumption. So we need some new lifestyle that uses less energy. So we need to engineer better stuff, less energy intensive stuff anyway. And every little bit helps not. So if we all make a point to turn out the lights, great. We can reduce this little sliver here. And we should all do that, make no mistake. But if we're going to do something, here's where you got to do it. Transport. Look, car, jet, transporting stuff. Those three together, huge chunk. So attack the problem at the biggest part first. Heating. Heating and cooling is another big chunk, and stuff is another big chunk. A little harder to get at. So if we were going to make changes, these are the things we would want to look at first. Public policy and engineering. So we need engineering to create better, more efficient options, and then we need private policy to drive people to use them. Like you were saying, maybe taxes would help encourage people to use more expensive kinds of energy. If it became equal to use, if it cost the same to use wind with petroleum, like OSU did, we even got a deal on it, why not? And then we're doing something good. So the focus of part 2 is how to engineer better stuff. And I want to give you a feel for how we go about attacking these problems, and then maybe we can get a handle on how much better can we make things better enough, and what would that take. So a real good example would be a car. So we all have cars, most of us have cars. Why does a car moving at a steady speed require any power to keep moving? So everything slows down if you don't apply energy. How many people think that's a contributing factor? Good? Yeah, everything slows down if you don't apply energy. There's friction, stuff like that. The car has to push wind out of the way. How many people think that's a contributing factor? Right. The wheels drag as they roll against the ground. Oh, there's that rolling friction. Right. The car is heavy. Right? You got to schlep a lot of mass around, especially if you keep a bunch of stuff in your car that you don't use. And something's got to power the stereo. So, right, all of that stuff. So there are all places that we can, as engineers, we can go in and try to understand the physics of these things, and which things can we control and reduce, and which things can we not control. So at steady speed, the car has to push the wind out of the way. That's wind resistance. The drag on the wheels rolling along the ground is rolling resistance. If you're going uphill, if you live in Colorado, half the time you're going uphill, it doesn't require potential energy. And when you go up a hill, you have to acquire potential energy. It takes energy to do that. So the energy to travel some trip of length d, here's the d, has these 3 terms. So one of them, this is the wind resistance term. And I believe the next slide will talk about what all these variables are. But we have a wind resistance, we have a rolling resistance, and we have the going uphill problem. Those are the 3 major contributors. And that contributes to the energy. But notice, wind resistance, which is, maybe it's here. If I do this, wind resistance, rolling resistance, and potential energy. Only the wind resistance depends on the velocity, v. So people say, well, if you didn't drive so fast, you would save energy. Right, but if you drove very, 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 very slowly, you would still be using energy because of these other terms. And notice it goes up as the velocity squared. So that, if you're an engineer, you're thinking, this changes quickly. If I can reduce v even a little bit, I get a lot of bang for the buck. So I'm going to look at trying to drive more slowly. Reduce that term. And also, this equation does not include the engine efficiency. So we need to account for that, because if we can make more efficient engines, clearly we will have more energy efficient vehicles. So here's a steady speed example. So let's say you get in the car, you drive at 60 miles per hour to Vail from Boulder, Colorado. I know you're going to do that. Rho is the density of air that you have to push out of the way. It appears here in the wind resistance term. So the density of the air, if you were trying to push water out of the way, this factor would be a lot bigger, but it's just air. 1 kilogram per cubic meter. Area, this is the frontal area of your vehicle. Maybe it's a square meter, depending on the size of what vehicle you're driving. So that appears here. If you had a vehicle that had a smaller frontal area, you could pick something up here. There's another factor in here we're going to come back to later. Rolling resistance, a typical number might be 0.01. It doesn't have any units. M is the mass of your vehicle. Maybe you've got a 1,000 kilogram vehicle. If you have a lighter vehicle, your rolling resistance will go down. Gravity you can't do anything about. S is the slope, going uphill to Vail. So if you're going uphill, here's the mass of your vehicle again. If your vehicle is lighter, you can save on this term as well. Can't do anything about gravity unless Vail is on the moon. And then there's other issues. And then the efficiency, this is the distance, this is the energy efficiency. It wasn't on the last slide. We put it in this one. Remember, when you divide by a small number, you get a big number. So if you have a low efficiency and it's in the denominator, it's going to increase the energy that you consume. So all's well with the world. Here's an SUV. This one has a frontal area of 1.5 meters square and a mass of 2,000 kilograms. So let's work it out. This one is worked out with the 1 meter squared area and 1,000 kilograms. So this is not an SUV, this is a smaller car. If we plug in all these numbers, what's the 1.3 kilogram per cubic meter? I'm expecting that was the density of air. Let me go back. That says 1. Maybe it's rounded off. Because I think this is 1/2. Rho is the density of air. A is your frontal area. Here is your velocity squared. 60 miles an hour is 30 meters per second, roughly. Here is your rolling resistance, your mass, your gravity. Here is the slope in miles per mile, going up to Vail, your mass and your gravity. And over there is the distance, so it's 160 kilometers, and say an energy efficiency of 0.25. When you work that out, that trip would work out to 160 kilowatt hours for that trip. If you had 4 people in the car, that's 40 kilowatt hours per person. I shouldn't say per day, it should say per person. And just to drive the point home, 103 of that is from this first term, 18 and 36. Which term is this? Wind resistance, 60 miles an hour. Here is your rolling resistance, and here is the fact that it's uphill. When you go down, your slope is negative. So you're picking up some potential energy. It's 100 to 120. Why is that? Because you're recovering some of your potential energy. If this is 160, why isn't this like half of that? Oh, you still got to brake and stuff like that. So what if you don't carpool? What if you drive yourself to Vail and you meet your friends there and they all drove? Don't do it. If we weren't climbing the mountains and the slope were 0, I can point better over here. If the slope here pointed to were 0, then this term would be gone. So if you're driving in Ohio to go skiing, you don't have this term, but you still have the rolling resistance. Rolling resistance is small compared to the wind resistance, about 20%. I wouldn't say it's insignificant, it's still about 20%. Okay, so energies look at this, the way engineers look at this, say, oh, I want to reduce this. So first thing I do is look at each term and figure out what can I reduce. So I look at each first thing I'm going to look at, if I want to reduce the wind resistance. Density of air, I can't change that. Reduce the frontal area of my car. I can do that. I'll make it, I don't know, small. I can reduce the frontal area, but volume is area times length. So if I make the front area small, and I still need room to carry my kids and my groceries, I need a long car to have the volume, right? So I'm looking at car designs that are long and skinny. If I want to still, I got to fit the skiers. Well, long and skinny is good for skis. That's okay. If I reduce A, it's good to increase the length of the vehicle to keep the volume. So the conclusion there is, as an engineer, if I want to be energy efficient, I want to make long, skinny vehicles. You don't see those out on the street? Just saying. Then I would say I want to reduce the velocity. I really want to reduce the velocity because the energy goes as a square velocity. So that's a big knob. Engineers say, oh, what knobs can I turn? We would call that a knob. If I turn that knob, it has a big impact. So if I could turn that knob down even a little bit, I get a huge payoff. Ooh, I want to reduce the velocity. I'm going to make people drive slow. Wish me luck. We have speed limits of 55. A lot of that came around during the energy crisis. You're too young to remember, but when I was young, we had an energy crisis, and then everyone, we used to drive at 65, 70 all the time. They set everything back to 55 to make us drive slowly. Who drives at 55? Nobody. You'd get killed if you did that. And you go to West Virginia, and the speed limit's 70 anyways. And they've got slopes. Wind resistance. So the car has to push the air out of the way. So the way McKay describes it is that The car is trying to create a tube that it can, because it has to displace the air, it's creating this tube, so it has to push the air out of the way, and the bigger the cross-section of your vehicle, the more air you've got to push. Now you have some control over that by the shape of the front of your car. If you can make it more aerodynamic so that it sheds the air more efficiently, you're going to push the air aside a little better, and there is a factor for that that's not on this slide, but we're going to get to it. But the bigger the cross section, then the bigger the tube, and the faster the vehicle goes, the harder it has to push. So I sometimes say, imagine if you needed to go to the corner store to get milk and you were the engine and you had to push the car. You're pushing the car, well, that takes a lot of energy, but you're pushing it so slowly that all you're feeling is the rolling resistance. You can't push that car, you can't run fast enough to start to really feel the wind resistance. But if you could, you'd really notice that. Maybe on a bicycle you could start to feel it, I don't know. And then so we looked at the wind resistance, and now I'm an engineer. I want to look at these other guys. So I want to reduce all of these. I want to reduce this. I want to reduce the rolling resistance. So I would like to reduce the coefficient. CRR stands for coefficient of rolling resistance. I could make really slippery tire. No, that's not a good idea, is it? That might be a little hard. But there's work that goes into tires. You have to make them sticky enough to be safe, but if you have too much friction, then you lose energy. I could reduce the mass of the vehicle, bing, bing, bing. That'd be a good one. But I still want it to be safe, so if somebody hits me, it doesn't, I don't want to make it out of paper. Gravitational constant, G, I can't adjust that, as long as I stay on this planet. The second, third term there, I could reduce potential energy changes. Well, I could reduce the slope. If I always drive downhill, I'm golden. When I was a kid, we were going to move to Brazil, and my dad said that we would drive there because it was downhill all the way. Then he found out we had to pay a tax at every border we crossed, so we didn't do it. Can't do much about slope, because if you go to the grocery store, it's downhill, you got to come home. Could reduce the mass of the vehicle, good idea. Gravitational constant is still not adjustable. I could reduce the distance that I drive. And I could increase the denominator, epsilon, the energy efficiency. And what else can we do? What's not shown in this equation?
How often you drive?
Well, that would be in the total distance that I drive. In the total distance that people drive. What's not here is how many people are in the car. Okay? Oh, yeah. Fancy arrows, whatever. All right, so here is a plot. This is energy consumption in kilowatt hours per 100 kilometers. So normalized to distance is what we would say. And this is speed, kilometers per hour, 0 to 20. Now, this here is the rolling resistance, and it looks like it's set at about, I'm guessing it looks like about 11. Maybe it's 10. The rolling resistance is constant. It does not depend on the speed. The slope term isn't in there. The air resistance is in here. If you're not traveling at all 0 miles per hour, no air resistance. You don't have to worry. If you're moving very slowly, it's not that big a deal. As you get up to, we said that 60 miles an hour was, that was in meters per second. So I don't know what 60 miles per hour is. What is it? Like 100-ish kilometers, somewhere like that. Air resistance is going up rapidly. And then the total is this. So how can I reduce the energy for that ski trip? Which of these things you think will contribute the most? Let's read what they are. Half the speed. If I cut my speed in half the frontal area, half the weight, half the rolling resistance, double the number of people in the car. Here's the equation. So which things will have the most effect? And it can be more than one thing. How many people say A? The speed? Okay, because you saw V squared. That's going to have a big impact. Half the frontal area, right? That's going to reduce this term by a factor of 2. Half the weight will reduce both of these by a factor of 2. Half the rolling resistance will reduce just this term. So that's not one of the answers. double the people in the car, or the energy efficiency, if I double this, this will reduce by a factor of 2. So even though this says, oh, it doesn't. Great. Oh, it says A or E is the right answer. A or E. Half the speed, that has a big effect, and double the people in the car or the efficiency, I claim that that has the same effect as the rest of these. Actually, oh, I know why. The reason that E has a bigger effect than the rest of these, like say you double the number of people in the car, is because that affects all of these terms. And if I half the weight, it only affects these 2 terms. If I half the frontal area, this term goes down by a factor of 2. But if I increase the efficiency, that has a bigger effect, or doubling the number of people in the car, because it multiplies all the terms. Having the speed alone would reduce the wind resistance by 75%. So out of the 160 kilowatt hours it took to get to Vail, about 77. Doubling the people in energy would have it overall, so 80 out of 160. So which of those things can the engineer control, and which of those things can the driver control? Speed and the number of passengers are directly controlled by the driver. So I, as the engineer, can't do anything about that. Others are indirectly controlled by the choice of vehicle. I could buy an SUV, or I could buy something long and pointy. Steady speed re-examined. So I said that the area, you could improve the effect of the area if it were aerodynamic. So here we're going to introduce something called the drag coefficient, C sub D. So if I have a vehicle that's a board, a big flat 1 meter square board on the front, that's going to have a certain air resistance. If I make it pointed or convex somehow, I can reduce the effective area because I made it more aerodynamic. So that's what that C sub D is. The worst case I'd make something concave, like a big scoop in the front, a shovel. That would be bad. So people choose ECDs to try to reduce that term. Efficient car, they might reduce the effective area by a quarter, by 3/4, sorry. So if the area of the vehicle, front area of the vehicle is 2 meters, 2 square meters, but you have a good drag coefficient, you can knock down the effective area, which is what we use in those equations, to a half. And then if I have 1 to 4 passengers, my area per person is those numbers. Typical car is more like a third. And a typical car has a frontal area of about 2.5 square meters. Bicycle has a high drag coefficient. It's not very aerodynamic, but it has a small area. Train has it's not that great aerodynamically, has 15 square meters, but when you do it per person, you get a huge benefit. Oh, we said something about a long, skinny vehicle. Huge volume there, can carry a lot of people. A bus, 0.45. The frontal area is 9, so the effective area is more like 4. And if you have 20 to 50 passengers, then you get pretty decent area per person. So A for bike is big, but the velocity is small. A for train is big, but it's shared by a lot of people. Can we do better? We need better aerodynamics. So that's what those aero guys over in the next building do. They figure out how to reduce the drag coefficient. Maybe some kind of a fairing or a shell to make the vehicle more aerodynamic, but of course it adds weight. Engineering trade-off. Here are some eco car type proposal things. Here is this car with the lid off. So look, long and skinny. It's wider in the back. It looks pretty aerodynamic. They don't give the drag coefficient for this. They claimed that this vehicle could go coast to coast on 4.5 liters of gas. With one person in it where they're sitting, I don't know. But you're not going to sell this to your neighbors in the suburbs, I don't think.
Is there a motor on that somewhere?
There's supposed to be. They just look like bicycle wheels. There's got to be an engine in it, because otherwise why would you use, unless the guy has to pedal too. I don't know. We'll have to look this up. Or you can have a small area. So here's a big honking SUV that gets 17 miles per gallon. Here's some kind of crazy eco car that gets 170 miles per gallon. Here it is on a staircase. So this is 1 person wide, right? If you could get people to accept driving with the passengers behind them instead of next to them, then you could make a huge, huge difference. Huge improvements are possible is what I'm going to claim. And here's pictures of some crazy long skinny vehicles to end the class with. This is 1 penny sheet. I don't know what that means. That's the name of the website. This is goofy looking. I think we have a theme here of goofy looking. Goofy looking. Long and skinny. Goofy looking. This is the Buckeye Bullet. It's not energy efficient, but it's long and skinny, and it's Ohio State. So I'm going to stop here. Are there any questions? Yes.
Is there a quiz tonight?
No, we canceled. There's a quiz due today, but the one that was going to be due next week, we're going to move that till after spring break. I forgot what the one today covers, but not Don Costin's lecture. That's the one that we're going to put till after the midterm. Okay? Any other different questions? Yes.
Do you suppose why we didn't do this type of thing earlier? It's just because we didn't know much about it? Because don't you think if we started building cars this way, that, maybe we would think this is normal rather than...
The equation that we've been discussing today
Yeah.
has been known for a long time. I think that people have known that you can make a car more energy efficient by making these kinds of shapes, but I don't think that anybody would want to make one, because if I made this car and you could go buy a Toyota Corolla, which would you buy? I would never be able to sell this. There isn't enough pressure yet.
No, I agree, but yeah.
That's my personal view. I think that people know how to do this, but the question is, can we get people to accept it? And when I go for a drive, I want to talk to my husband. I don't want to hear him from behind me, or me behind him. But maybe I'm going to have to learn to live with that. All right, run and play. We'll see you Monday.